Here is the sampling distribution. What we have is the normal distribution of the entire population, and that is the area under the curve. So if we look at the entire population, we can take out samples. So this is sample 1, sample 2, sample 3, and we can take out many more. So by taking out each samples, we can calculate the sample mean. So once again, this is the population, and we're taking out a sample of the population and calculating the sample mean. So in conclusion, we're calculating the mean of the sample group from the population. That's what we're doing. So here's an example. Samples of 25 computer chips are randomly selected from a factory regularly for quality control checking. The mean lifetime of computer chips is 1,000 hours and a standard deviation of 80 hours. It is reasonable to assume the lifetime of computer chips follows a normal distribution. Use X to denote the lifetime of a computer chip and X bar to denote the lifetime of the sample of 25 computer chips. All right, seems like there's a lot of information. Doesn't matter. We can identify the key elements first. So mu is the mean. So it is the mean lifetime of computer chips, and that'll be 1,000 hours. And the sigma, that is standard deviation, 80 hours. So we'll put 80 here. N is the sample size. So we're taking a sample of 25 computer chips, 25. So the first question, the mean of the sample lifetime is, here's the equation. So E is the expectation, which we mentioned earlier. And this is the mean because expectation is the mean. And that equals to the population mean, which is mu. So we can put in the number 1,000, and the expectation of X bar would be 1,000 hours. The variance of the sample mean lifetime will be given us this equation. So the variance is just the standard deviation squared, but this time we need to take the N into consideration. So it'll be standard deviation squared over the N. So N is 25. So we put 80 here squared, and we have 256 hours. Next, we have the standard error of sample mean lifetime, and that is just the square root of the variance. So what you could do, you could just go 256 square root, or you could put it into this equation. So this is 80 over square root of 25, and that is 16 hours. What happens if we do not have a sample mean? Instead, we have sample proportion. So assume that among all travelers, 40% of the travelers are frequent flyers. If a random sample size of 70 is selected, and each time the sample proportion of frequent flyers is calculated and denoted as p hat, the first thing that we should do, we need to identify the p proportion. So proportion would be the 40%, which is 0.4. So 40 divided by 100, and we get 0.4. Sample size is 70, so N is 70. So the first question, what is the sample proportion of frequent flyers? So the expectation of p hat, that is the sample mean, or you can call it sample proportion, because we're no longer using the mean anymore. So the expectation of proportion is p, that is 0.4. We just put it in directly. And what is the variance of sample proportion? So this is the equation, p times 1 minus p over n. And we put the numbers in. So p is 0.4, and 1 minus 0.4 is 0.6 over 70. So we have 0.0034. Similar to the previous question, if they ask for standard error of the variance, we can just square root the variance. So you can go 0.0034 square root of that. Or you can put everything into this equation. So SE of the p hat. We put 0.4 times 1 minus 0.4 over 70 and square root everything, and you should get the answer, 0.05855.